This is a technical briefing on the weaponization of electromagnetic proximity detection in naval air defense, specifically the variable time fuse, designated VT. What you're about to hear is the forensic deconstruction of a technological turning point that redefined air superiority in the Pacific theater. In early 1942, Imperial Japanese Navy pilots operated under a tactical certainty that bordered on doctrinal arrogance. They had observed American anti-aircraft fire at Coral Sea, at Midway, and during the Guadalcanal campaign. Their assessment was clinically accurate. American gunners were statistically irrelevant. A Mitsubishi A6M0 pilot could initiate a high-speed evasive dive, execute a snap roll at terminal velocity, and watch American 5-inch shells detonate hundreds of meters behind his flight path. The shells were predictable. The fuses were mechanical. The kill probability was negligible. Japanese after-action reports from 1942 document this contempt with precision. One IJN flight leader described American AA fire as fireworks without consequence. Another noted that American gunners were slaves to the clock, referring to the mechanical time fuses that required manual calculation of shell flight time, target altitude, and projected intercept point. By the time a shell reached the calculated detonation altitude, a competent pilot had already altered course, speed, and vector. The mathematics were simple. Human reaction time plus mechanical fuse delay equaled tactical irrelevance. The numbers confirm this assessment. In 1941, U.S. Navy statistical analysis determined that it required an average of 10,000 rounds of anti-aircraft ammunition to achieve a single aircraft kill. 10,000 shells. One kill. This was not a gunnery problem. This was a physics problem. Traditional AA munitions relied on two fuse types, impact and mechanical time. Impact fuses required a direct hit on an aircraft traveling at 300 knots, executing three-dimensional evasion maneuvers. The probability of impact was functionally zero. Mechanical time fuses required the gun crew to estimate target altitude, calculate shell flight time, manually set the fuse timer, load the shell, and fire, all while the target maneuvered unpredictably. By the time the shell reached its preset detonation point, the target had relocated to a different section of airspace entirely. The Japanese pilot's confidence was not arrogance. It was mathematics. They had correctly identified that American anti-aircraft doctrine was built on a broken foundation. The human operator could not process targeting data fast enough. The mechanical fuse could not adapt to evasive maneuvers. The result was a sky filled with exploding shells and untouched aircraft. The Imperial Japanese Navy entered 1943 convinced that American air defense was a solvable problem, a problem they had already solved through superior pilot training and aircraft maneuverability. They were wrong. What they did not know, what they could not have known, was that a classified research group operating under the codename Section T had already designed the weapon that would dismantle their tactical doctrine. The variable time fuse was not an incremental improvement, it was a paradigm shift. It transformed every anti-aircraft shell into an autonomous hunter. It eliminated the human error variable. It rendered evasive maneuvers irrelevant. And it did so using a technology so advanced that the U.S. Navy classified it above top secret, restricting its use to oceanic combat zones to prevent enemy reverse engineering. This is the technical story of how a miniaturized radio transmitter, a ruggedized vacuum tube, and a proximity sensor turned the Pacific theater into a graveyard for Japanese naval aviation. This is the story of the VT Fuze. Chapter 1. The Accuracy Gap. Let's establish baseline performance metrics for traditional anti-aircraft systems in the early Pacific War. We're not discussing incompetence. We're discussing the hard limits of mechanical targeting systems against high-speed aerial threats. The U.S. Navy entered World War II with two primary AA fuse technologies: Mark 51 mechanical time fuses and contact impact fuses. Both were World War I-era solutions, adapted for a World War II-era threat environment. The performance gap was catastrophic. Start with mechanical time fuses. The operational sequence was as follows. Fire control radar or optical rangefinders determined target altitude and bearing. A human operator calculated estimated shell flight time to intercept altitude. A second operator manually adjusted the fuse timing mechanism on each individual shell. The shell was loaded and fired. The fuse timer initiated at launch, counted down during flight, and detonated the bursting charge at the predetermined time. The lethal radius of a 5-inch high-explosive shell was approximately 50 meters. If the aircraft was within that radius at detonation, fragmentation damage was probable. The problem was not the explosive. The problem was the timer. Mechanical time fuses used a clockwork mechanism, a literal spring-wound gear train that initiated at the moment of firing. The gunner set this timer by rotating a collar on the fuse body, adjusting the delay in quarter-second increments. This required the gunner to predict not just where the aircraft would be, but when it would be there, within a quarter-second margin of error, while the aircraft executed evasive maneuvers at 300 knots. The human nervous system cannot process three-dimensional aerial movement fast enough to make these calculations accurate. Cognitive processing delay for visual target acquisition is approximately 200 milliseconds. Add motor response time for manual fuse adjustment, another 150 milliseconds. Add communication lag between the rangefinder operator and the fuse setter, another 200 milliseconds. You're now operating with a minimum half-second delay between target observation and fuse setting. In that half-second, a zero traveling at maximum speed has displaced 125 meters. Your calculated intercept point is already obsolete before the shell leaves the barrel. Now layer in the mechanical limitations of the fuse itself. The clockwork timer mechanism was sensitive to G-forces. A 5-inch gun firing at maximum elevation subjects the shell to approximately 20,000 Gs of acceleration in the first millisecond of launch. This force distorts the gear train, introduces microfractures in the spring mechanism, and degrades timing accuracy. Field testing revealed that mechanical time fuses had a timing variance of plus or minus 1 full second under combat conditions. A 1-second error at shell velocities meant your detonation point could be off by 800 meters vertically. You weren't missing the aircraft. You were missing the altitude band entirely. Impact fuses were even less effective. These fuses required direct contact with the target to initiate detonation. The cross-sectional area of a Mitsubishi A6M0 is approximately 14 square meters. The cross-sectional area of a 5-inch shell is 0.013 square meters. You are trying to hit a 14 square meter target with a projectile that occupies 1/1000th of that area, while both objects are moving at supersonic and near-supersonic speeds, respectively, in three-dimensional space, with the target actively evading. The probability mathematics are brutal. Even with radar-directed fire control, hit probability against a maneuvering target was estimated at 0.002% per shell. You could fire 500 shells and statistically expect one impact. The U.S. Navy's own Bureau of Ordnance calculated that during the first year of the Pacific War, American ships expended over 50 million rounds of anti-aircraft ammunition. Confirmed aircraft kills attributed to shipboard. A of fire, approximately 2,500. That's a 20,000 to 1 expenditure ratio. You were burning through ammunition faster than industrial production could replace it, and you were still losing carriers to Japanese air attacks. The Japanese understood this. Their tactical doctrine explicitly capitalized on AA inefficiency. IJN strike packages used high-speed ingress, split formation attacks, and coordinated evasion patterns designed to maximize the time American gunners spent recalculating fuse settings. A single zero could occupy an entire gun crew for 15 seconds of continuous fire without sustaining damage, simply by executing a randomized evasion sequence. Multiply that across a 40-aircraft strike package, and you've paralyzed an entire carrier group's air defense network. The Battle of Santa Cruz in October 1942 provided the clearest demonstration of this accuracy gap. The carrier, USS Hornet, was attacked by multiple waves of IJN aircraft. American gunners fired over 16,000 rounds of 5-inch ammunition during the engagement. Confirmed kills: 11 aircraft. The Hornet was struck by 3 bombs, 2 torpedoes, and 2 kamikaze impacts. She sank 6 hours later. The AA fire was sustained, aggressive, and tactically irrelevant. The Japanese lost 11 aircraft. The U.S. lost a fleet carrier. This was the operational reality that confronted the U.S. Navy in 1943. You could not outshoot the problem. You could not outtrain the problem. The problem was foundational. Mechanical fuses required human prediction of future target location. Humans cannot predict the future. Therefore, mechanical fuses cannot reliably intercept maneuvering aircraft. The logic was airtight. The kill ratios proved it. What the Navy needed was a fuse that didn't rely on prediction, a fuse that sensed the target in real time and detonated autonomously when the target entered lethal radius, a fuse that eliminated the human calculation variable entirely. That fuse would require technology that didn't exist in 1941. It would require miniaturization of radio components that were currently the size of filing cabinets. It would require vacuum tubes that could survive forces that shattered steel. It would require a power source that could fit inside a shell casing and operate for the 8-second flight time of an AA round. The U.S. Navy tasked Section T with making the impossible routine. Chapter 2: Section T and the Miniature Radar. Section T was a classified research group operating under the National Defense Research Committee, established in 1940 and headquartered at the Applied Physics Laboratory in Silver Spring, Maryland. The designation Section T stood for Section Tango in naval parlance, but operationally it referred to one thing: proximity fuse development. The project objective was explicit: design a fuse mechanism that could detect aircraft proximity and initiate detonation without mechanical timers or human input. The concept was theoretically sound. Radio waves travel at the speed of light. If you could mount a miniature radio transmitter inside an artillery shell, have it emit a continuous signal, and detect the reflected signal when it bounced off an aircraft, you could measure the distance to the target in real time. When that distance decreased below lethal radius, 50 meters for a 5-inch shell, you triggered the detonation circuit. The aircraft wouldn't need to be hit. It only needed to be near. The fuse would do the rest. The engineering problem was that every component required for this system was physically impossible to manufacture at the required scale in 1940. Start with the radio transmitter. A functional radio transmitter requires an oscillator circuit to generate the radio frequency signal, an amplifier to boost signal strength, and an antenna to radiate the electromagnetic wave. In 1940, the smallest radio transmitter in operational use was the SCR-194 man-pack radio, which weighed 35 pounds and required a backpack-mounted battery. Section T needed to fit equivalent functionality into a fuse body measuring 2 inches in diameter and 4 inches in length. You weren't miniaturizing the radio, you were reinventing it. The core challenge was the vacuum tube. All radio transmitters in 1940 used vacuum tubes as the active amplification element. A vacuum tube is a glass envelope containing a heated cathode that emits electrons, a control grid that modulates electron flow, and an anode that collects electrons. The electron flow generates the amplification effect that makes radio transmission possible. The problem: vacuum tubes are fragile. The glass envelope shatters under impact. The internal filament breaks under vibration, and a 5-inch naval gun subjects the shell to 20,000 Gs of acceleration at firing. That's 20,000 times the force of gravity applied in the first 15 milliseconds of launch. Standard vacuum tubes disintegrated under these forces. Section T engineer James Van Allen led the tube ruggedization effort. The solution was a complete redesign of vacuum tube architecture. The team developed the VT 158 miniature tube, which used a ceramic base instead of glass for structural integrity, a reinforced tungsten filament capable of withstanding shock loads, and a spring-mounted internal structure that allowed the filament to flex under G-forces without fracturing. Each tube was tested to failure in a centrifuge, then redesigned based on failure mode analysis. The final VT 158 tube could survive 30,000 Gs of acceleration and still maintain amplification characteristics. It was the most advanced vacuum tube ever manufactured at the time. But surviving the launch was only the first problem. The tube also needed to function during flight. The shell rotates at 300 revolutions per second due to barrel rifling, generating centrifugal forces that pull components away from the central axis. The tube needed to operate while being spun at 18,000 RPM. Additionally, the shell experiences aerodynamic heating during flight, raising internal temperatures to over 100 degrees Celsius. The tube needed to maintain stable electrical characteristics across a 100-degree temperature gradient, and it needed to do all of this for 8 seconds, the maximum flight time of a 5-inch shell to maximum effective range. The power supply was the second engineering nightmare. The radio transmitter required approximately 3 watts of continuous power. A standard flashlight battery could provide this, but batteries are heavy, and weight is prohibitive in artillery shells. Every gram of payload reduces muzzle velocity and effective range. Section T needed a power source with energy density higher than any existing battery technology. The solution was a reserve battery design using a liquid electrolyte that was inert until activation. The battery consisted of layered zinc and silver plates separated by absorbent paper. In storage, the battery was dry and inactive. At the moment of firing, a spring-loaded mechanism punctured a sealed vial of potassium hydroxide electrolyte, which flooded the cell stack and activated the battery. The battery reached full output voltage within 50 milliseconds of firing and sustained output for 12 seconds, long enough to power the transmitter for the entire flight. The reserve battery design added only 60 grams to the fuse assembly. The radio circuit itself used a Doppler-effect sensing mechanism. The transmitter emitted a continuous radio wave at 180 megahertz. When this wave reflected off a metallic surface, an aircraft, and returned to the shell, the frequency of the reflected signal was shifted due to the Doppler effect. The shell was moving toward the aircraft, so the reflected signal had a higher frequency than the transmitted signal. A mixer circuit combined the transmitted and reflected signals, and the difference frequency was fed into a detector circuit. When the difference frequency indicated that the range to the target had decreased below the threshold distance, the detector triggered the detonation circuit. This was not a simple proximity detector. This was a miniature radar system capable of autonomous target discrimination. The circuit could distinguish between an aircraft and the ocean's surface based on the Doppler signature. It could reject false triggers from rain, chaff, and shell fragments from other detonations. And it could make the detonation decision in less than 10 microseconds, faster than any mechanical switch could operate. The final assembly was a masterpiece of compact engineering. The complete VT Fuze measured 2 inches in diameter and 4 inches in length. It contained 5 miniature vacuum tubes, a reserve battery, a transmitter circuit, a receiver circuit, a mixer stage, a detector circuit, and a detonation relay. The entire assembly weighed 150 grams, less than a third of a pound. It could survive being fired from a 5-inch naval gun, operate while spinning at 18,000 RPM, detect an aircraft at ranges up to 100 meters, and initiate detonation within lethal radius with a timing precision of 10 microseconds. The first successful test firing occurred in August 1942 at the Dahlgren Naval Proving Ground. A 5-inch shell equipped with a VT Fuze was fired at a radio-controlled target drone. The shell passed within 30 meters of the drone. The fuse detected the proximity, initiated detonation, and the fragmentation blast destroyed the drone. No direct impact, no human timer calculation. The shell sensed the target and killed it autonomously. The test observers described it as watching a shell hunt the aircraft. By January 1943, the VT Fuze was in mass production. Operationally, it was designated the Mark 53 for 5-inch shells and Mark 32 for 3-inch shells. Security classification was above top secret. Personnel with access to VT Fuze specifications required compartmentalized clearance. The fuses were transported in sealed containers with armed guards, and the Navy issued a standing order. VT fuses could only be used over water, where duds would sink and could not be recovered by enemy forces. The Japanese had no idea what was coming. Chapter 3. The Marianas Turkey Shoot. The Battle of the Philippine Sea, June 19th to 20th, 1944, was the operational debut of the VT Fuze as a theater-scale air defense weapon. The Imperial Japanese Navy committed 9 carriers and 470 aircraft to a decisive engagement intended to cripple American carrier forces near the Mariana Islands. The Japanese plan relied on superior pilot skill, extended range of land-based air support, and the proven ineffectiveness of American anti-aircraft fire. The plan disintegrated within 4 hours of first contact. The American force comprised 15 carriers and 956 aircraft, supported by the most concentrated anti-aircraft defense network ever deployed in naval warfare. Every 5-inch gun in the task force was loaded with VT fused ammunition. The Japanese did not know this. Their pre-battle intelligence still assessed American AA fire using 1942 performance data. They were flying into a weapon system that had evolved 2 generations beyond their tactical assumptions. The first Japanese strike wave launched at 0830 hours. 69 aircraft composed of Zero fighters, Val dive bombers, and Jill torpedo bombers. The strike formation approached Task Force 58 in a standard dispersed attack pattern, designed to split American fighter coverage and overwhelm AA defenses through simultaneous multi-axis attacks. Japanese pilots had used this doctrine successfully at Coral Sea and Santa Cruz. It should have worked. At 0930 hours, the Japanese strike package entered AA range at 40,000 meters. American radar directors acquired the formation and began feeding targeting data to the gun crews. The 5-inch guns opened fire at 35,000 meters, extreme range, but within VT Fuze effective radius. The first shells detonated in proximity to the lead aircraft section. 3 Zeros disappeared from radar. The Japanese formation did not react. They assumed the detonations were standard timed fuses and continued their approach. At 30,000 meters, the American fire intensified. Every 5-inch mount was now engaged, firing at a sustained rate of 15 rounds per minute per gun. The VT fuses were functioning exactly as designed. Shells that passed within 50 meters of an aircraft detonated autonomously. The fragmentation patterns were overlapping, creating a defensive barrier of continuous airbursts. Japanese pilots initiated evasive maneuvers, the same high-speed diving breaks that had been effective in previous engagements. The maneuvers were irrelevant. The shells didn't need to track the evasion. They only needed proximity. A Zero could break left at 6 Gs, but if a VT-fused shell passed within 50 meters during the maneuver, the aircraft was inside the kill zone. The Japanese formation began disintegrating at 25,000 meters. Pilots reported that American shells were detonating too close and without reason. The shells were not hitting the aircraft, they were exploding near them. and the aircraft were still being destroyed. This was outside the tactical model. Mechanical time fuses did not behave this way. The pilots assumed the Americans had developed a new fuse setting technique, but they could not identify the mechanism. They continued the attack. By the time the first wave reached 15,000 meters, the altitude at which they would normally begin their terminal attack dive, 42 of the original 69 aircraft had been destroyed. Not damaged, destroyed. The remaining 27 aircraft pressed the attack, but their formation cohesion was gone. Individual pilots were now focused on survival, not targeting. The attack achieved negligible results. 2 aircraft managed to release ordnance. Both missed. The entire strike wave was effectively neutralized. The second Japanese strike wave launched at 1000 hours, 130 aircraft. This wave carried revised tactical instructions based on the first wave's reports. Approach at lower altitude to reduce AA exposure time, execute high-speed terminal runs, and do not attempt evasive maneuvers. Maintain speed and close as quickly as possible. The revised tactics assumed that American gunners had simply improved their mechanical fuse accuracy. The pilots believed they could defeat this through speed and aggression. They were wrong again. The VT Fuze did not care about altitude or speed. Proximity was proximity. The second wave was engaged at 30,000 meters. The kill rate was higher than the first wave because the aircraft were in a tighter formation, allowing multiple shells to engage multiple targets simultaneously. Japanese pilots described American AA fire as a wall of explosions. One surviving pilot reported that he saw 7 aircraft destroyed in a single 3-second span, all by shells that appeared to miss and then detonated in proximity. He described it as invisible death. The second wave lost 97 aircraft before reaching attack range. The surviving 33 aircraft broke off and attempted to withdraw. 16 were destroyed during the withdrawal phase. Total ordnance delivered to American ships, 0. The third wave launched at 1300 hours, 47 aircraft. This wave was a desperation strike. The Japanese fleet commander knew the first 2 waves had been annihilated, but he was committed to the engagement. The third wave was given no revised tactics. The pilots were simply ordered to attack. They understood they were being sent into a massacre. The third wave was destroyed in its entirety. Not a single aircraft reached attack range. The VT Fuses killed them at distances where Japanese pilots could not even visually acquire their targets. The battle had become industrialized slaughter. American gun crews were not aiming. They were area saturating. The VT Fuses were handling target discrimination and detonation timing autonomously. The human operators were simply loading shells and maintaining fire rate. By 1600 hours, the Battle of the Philippine Sea was effectively over. The Imperial Japanese Navy had launched 470 aircraft against Task Force 58. 315 were destroyed. Of those 315, approximately 240 were confirmed kills attributed to shipboard anti-aircraft fire. The VT Fuze had achieved a 5-to-1 improvement in kill efficiency over mechanical time fuses. The 10,000 rounds per kill ratio from 1942 had collapsed to approximately 200 rounds per kill in 1944. The same guns, the same ships. The only variable was the fuse. Japanese after-action reports from surviving pilots described the battle in terms of technological incomprehension. They knew they were being killed by proximity detonations, but they could not understand the mechanism. Some pilots theorized that American shells contained optical sensors. Others believed the Americans had developed a new type of explosive that detonated based on air pressure changes. None identified radio proximity detection, because miniaturization of radio components to that scale was assumed to be physically impossible. The Imperial Japanese Navy never recovered from the Philippine Sea. The loss of over 300 aircraft and the associated pilots many of whom were veteran combat aviators, represented an irreplaceable degradation of capability. More critically, the battle destroyed Japanese confidence in their tactical doctrine. If evasive maneuvers no longer provided protection from anti-aircraft fire, then the core assumption of IJN air attack strategy was invalid. Pilots could no longer trust their training. The psychological effect was as devastating as the material losses. American forces continued to use VT fuses in every subsequent Pacific engagement. The fuses remained classified, and recovered duds were aggressively secured to prevent enemy reverse engineering. Japanese intelligence never fully understood the mechanism before the war ended. They knew American anti-aircraft fire had become lethal. They did not know why. The Battle of the Philippine Sea is remembered as the Marianas Turkey Shoot in American naval history. The nickname trivializes what was actually a demonstration of technological supremacy so absolute that it rendered an entire enemy weapons system obsolete. The Japanese did not lose because their pilots were inferior. They lost because the Americans had changed the physics of air defense. The VT Fuze was not an incremental improvement. It was a paradigm shift that redefined what anti-aircraft fire could achieve. Chapter 4. The Security Blackout. The VT Fuze was the most closely guarded weapons technology of World War II. Its classification level exceeded the Manhattan Project in certain operational contexts, specifically regarding security protocols for preventing enemy acquisition of intact fuses. The Office of Naval Intelligence assessed that if a single VT fuse was recovered by Japanese or German forces and reverse engineered, Allied naval forces would lose their air defense superiority within 6 months. This assessment drove security measures that bordered on paranoia. The primary security directive was the over-water-only restriction. VT fuses could not be used in any combat environment where duds could be recovered by enemy forces. This meant no use over land, no use in shallow coastal waters where duds could be retrieved by divers, and no use in any theater where enemy ground forces might capture unexploded ordnance. The restriction was absolute. Violation required authorization from theater command level or higher. The only exception was the Battle of the Bulge in December 1944, when German forces broke through American lines in the Ardennes. General Eisenhower authorized the use of VT fuses in ground-based artillery to blunt the German offensive. The authorization was granted because the tactical emergency outweighed the security risk, and because Allied intelligence assessed that Germany lacked the industrial capacity to reverse engineer and mass-produce VT fuses before the war ended. The restriction was enforced through physical control of the fuses themselves. VT fuses were stored in separate magazines from conventional ammunition, under guard by Marine security detachments. Issue of VT fuses required written authorization from the ship's gunnery officer and the executive officer. Expended brass casings from VT fused shells were collected, counted, and documented. If a gun crew fired 100 VT fused rounds, the ship's records had to account for 100 expended casings. Any discrepancy triggered a security investigation. Pilots flying over areas where VT fuses had been used were briefed to report any sightings of unexploded ordnance floating in the water. Recovery teams were dispatched to retrieve duds whenever possible. The overwater restriction had a strategic side effect. It limited VT fuse use to naval and amphibious operations, which meant the weapon was optimized for the Pacific theater, where most combat occurred over open ocean. In the European theater, where ground combat dominated, VT fuses saw limited use until late 1944. This created a technological imbalance. The Pacific Fleet had a decisive air defense advantage, while ground forces in Europe continued to use mechanical time fuses for the majority of the war. The Japanese never successfully developed a proximity fuse. Japanese researchers were aware of the theoretical concept. Radio proximity detection was not secret science, but they lacked the miniaturization technology required to implement it. Specifically, Japanese vacuum tube manufacturing was years behind American capabilities. The smallest vacuum tube in Japanese production was the 1T4, used in portable radios, which measured 10 millimeters in diameter. This was too large to fit inside a fuse body and too fragile to survive gun launch forces. Japanese engineers attempted to develop ruggedized miniature tubes, but the material science requirements exceeded their industrial capacity. High-purity ceramics for tube bases were unavailable. Tungsten filament wire with the required tensile strength could not be manufactured at scale. The spring mounting systems needed to protect the filament during launch required precision machining that Japanese facilities could not achieve under wartime production constraints. Japanese intelligence did recover fragments of VT fuses from crashed American aircraft and from unexploded ordnance in shallow water near island bases. Forensic analysis of these fragments confirmed that the fuses used radio transmission, but the circuits were too damaged to reverse engineer. Even if intact fuses had been recovered, Japanese industrial capacity in 1944 was collapsing under strategic bombing and resource shortages. Mass production of VT fuses required a functional electronics industry, precision machining capability, and secure supply chains for exotic materials like tungsten and high-purity quartz. Japan had none of these in sufficient quantity. The Germans came closer. German researchers at the Rheinmetall facility developed a prototype proximity fuse in 1944, designated the Kranich device. The Kranich used a similar radio proximity detection principle, but the German design was larger and heavier than the American VT fuse, and it required external power from the gun's fire control system, which limited it to specific gun types. Critically, the Kranich was never deployed operationally. Production was delayed by Allied bombing of German industrial facilities, and by 1945, the Wehrmacht was in full retreat and had no capacity to integrate new weapons systems. A small number of Kranich fuses were manufactured, but none saw combat use. The technological gap between the VT fuse and Axis proximity fuse efforts was not a gap in theoretical understanding. It was a gap in industrial implementation. The Americans had the manufacturing precision, the material science base, and the supply chain security to mass-produce a device that required tolerances measured in microns and materials sourced from global supply networks. The Japanese and Germans understood what needed to be done. They simply could not do it at scale under wartime conditions. Post-war analysis by Allied intelligence estimated that if Japan had acquired a functional VT fuse in 1943 and successfully reverse-engineered it, they could have deployed an equivalent system by mid-1945 at the earliest. By mid-1945, the Japanese carrier fleet had been destroyed. Japanese naval aviation was reduced to kamikaze operations, and American forces controlled the air and sea around the Japanese home islands. Even if Japanese VT fuses had been fielded, they would have had minimal strategic impact. The technological advantage window had already closed. The VT fuse remained classified top secret until 1950. Even after the war ended, the U.S. military assessed that proximity fuse technology provided such a decisive advantage that public disclosure would harm national security. The technology was not declassified until the outbreak of the Korean War, when the military needed to expand production and could no longer maintain the security blackout on the underlying science. The security protocols surrounding the VT fuse were not paranoia. They were recognition that a single device, if compromised, could erase a multi-year technological lead. The overwater restriction cost American ground forces a valuable air defense tool for most of the European campaign, but it ensured that the Pacific Fleet retained unchallenged air superiority through 1945. That trade-off was calculated and deliberate. The U.S. Navy determined that losing tactical flexibility in Europe was acceptable if it preserved strategic dominance in the Pacific. The restriction was never violated except under direct authorization from theater command. The VT Fuze was not just a weapon, it was a strategic asset, protected with security measures normally reserved for nuclear weapons designs. The fact that the Japanese never acquired one, despite desperate intelligence efforts, is a testament to the effectiveness of those measures. Outro. The Kenneth Assessment. Final analysis. The variable time fuse was a clinical solution to a tactical deficiency. Japanese pilots did not lose to better trained gunners. They did not lose to heavier volume of fire. They lost to a glass tube and a radio wave. The VT Fuze removed the human prediction variable from anti-aircraft fire, replacing it with autonomous electromagnetic proximity detection. Once that replacement occurred, evasive maneuvers became statistically irrelevant. The shell did not need to predict the aircraft's future position, it only needed to sense the aircraft's current position. That technological distinction was the difference between a 10,000 to 1 kill ratio and a 200 to 1 kill ratio. The Imperial Japanese Navy entered the Battle of the Philippine Sea in June 1944 with the same tactical doctrine that had been effective in 1942. That doctrine assumed American anti-aircraft fire was predictable and survivable. The assumption was outdated by 2 years. The result was the destruction of over 300 aircraft in a single engagement. Japanese naval aviation never recovered. The Battle of the Philippine Sea was not a victory of superior tactics. It was a demonstration of technological overmatch. The VT Fuze was not an isolated innovation. It was the convergence of multiple technological advancements: miniaturized vacuum tubes, ruggedized electronics, reserve battery chemistry, radio frequency engineering, and high-speed detonation circuits. Each of these technologies required years of research and industrial refinement. The fact that American industry could mass-produce these components, integrate them into a functional weapons system, and deploy them at scale within 2 years of initial concept is the actual strategic lesson of the VT Fuze program. The weapon itself was impressive. The industrial capacity that manufactured it was decisive. Japanese and German attempts to replicate the VT Fuze failed not because their scientists were inferior, but because their industrial base could not support the manufacturing precision required. The VT Fuze was a product of material abundance, secure supply chains, and advanced manufacturing infrastructure. Those advantages were not replicable under wartime conditions by nations that were already resource-constrained and under sustained strategic bombing. The VT Fuze was a weapon that could only be built by a nation with intact industrial capacity. That fact alone made it a strategic weapon, not just a tactical one. The security protocols that restricted VT Fuze use to overwater engagements were justified by post-war outcomes. The Japanese never reverse-engineered the technology. The Germans came close, but ran out of time. The overwater restriction imposed tactical limitations, but it preserved strategic advantage. The calculation was correct. The VT Fuze remained in service for decades after World War II. Modern proximity fuses use solid-state electronics instead of vacuum tubes and digital signal processing instead of analog circuits, but the underlying principle remains identical. Detect proximity, calculate optimal detonation point, initiate bursting charge autonomously. The VT Fuze established the template for autonomous air defense systems that continues through current-generation surface-to-air missile systems. If there is a broader lesson here, it is this: weapons technology is not about superior firepower. It is about removing human limitations from the kill chain. The VT Fuze succeeded because it eliminated the requirement for human prediction. Modern autonomous weapons systems continue this trajectory. They sense, decide, and execute faster than human operators can process information. The VT Fuze was the first operational example of this principle at scale. The Japanese did not mock American anti-aircraft fire because they were arrogant. They mocked it because the criticism was statistically valid in 1942. By 1944, the criticism was obsolete. The Americans had changed the rules. The Japanese continued flying as if the old rules still applied. That disconnect cost them 300 aircraft in a single day. Briefing closed. Stay sharp.